So Isaac Newton is generally regarded as one of the greatest physicists ever. He wrote a book on optics and mechanics, which is the science of how things moved. He invented calculus to explain the things that he was trying to do in mechanics. And he knew all about Galileo and Kepler's discoveries. And he wanted to understand what are the underlying physical laws that could make sense of the patterns his predecessors have discovered. Why, for example, should planets move in ellipses rather than some other shape, maybe a figure 8 or a square? What causes them to move in that particular shape? This is the scientific question. Why does something behave the way it does? Newton is also responsible for unifying the laws that explain the behavior of planets and the things on Earth. And today, scientists take it for granted that the laws of nature are basically the same everywhere. But before Newton's time, there was no reason to assume that things that happened up in the sky, up in the heavens, behaved in the same way as things did on Earth. Now, the most fundamental of Newton's laws are his 3 laws of motion. And in getting these, Newton built on the work of Galileo. The 3 laws apply to any matter, not just planets, and they deal with the way motions are related to forces. So Newton's first law, and you should have these memorized, states that a body remains at rest or moves in a straight line at a constant speed unless acted on by an outside force. So before Newton, it had been widely held that objects had a natural tendency to stop moving, and he recognized there was this role of friction in stopping things, and realized that friction itself is a force. If you take away friction, like in space for example, things keep moving indefinitely. Another consequence of Newton's first law is that you need a force to change the direction of motion, such as going around a bend or around an orbit. Law 2 states the acceleration of an object is proportional to the force acting on the object. It's the most mathematical of the laws, and it's sometimes written as force is equal to mass times acceleration, or F equals ma. So the force here could be a push, it could be gravity, it could be magnetism, air pressure, friction, whatever. An acceleration is the rate of change of velocity. And for physicists, braking is a form of negative acceleration. The mass of a body is the amount of matter it contains. Loosely speaking, it's similar to a body's weight. Mass is not the same as volume, which is essentially the size of an object. So for example, if I have a handful of shaving cream, as it expands, the mass stays the same, but the volume may increase. The length between mass and volume is density. Density is mass over volume. So things like iron have a high density, air has a low density. And the other thing that F equals ma implies is that acceleration is in the same direction as force. Now this equation looks simple, but as any of my physics students soon find out, mechanics gets very complicated when a single object is acted on by several forces, or when we have to consider a complicated object made out of many small ones. Newton's laws show us how very complicated motions are actually the result of simple interplays between force and mass. This is called the analytical aspect of science. Law 3 states that whenever one body exerts a force on a second body, the second body exerts an equal and opposite force on the first body. You've often heard this as for every action, there's an equal and opposite reaction. So, if I shoot a gun, the recoil of the gun is an example. There's a force pushing the bullet one direction, and the bullet pushes back on the gun the other direction. Or if I jump off a skateboard, as I jump off, I'll go one direction, and the skateboard will go on the other direction. Now, the other great law that Newton came up with is not called the fourth law because it deals with one particular kind of force. The first 3 laws are completely general and deal with all kinds of forces. So his next law that he is known for is called the law of gravity. 2 bodies attract each other with a force that's directly proportional to the product of their masses and inversely proportional to the square of the distance between them, where F is g, where g is called Newton's gravitational constant. We just look it up. Mass of one object, mass of the second object, divided by the distance between them squared. So before Newton, gravity was a force produced by the Earth and nothing else. But when Newton thought about the implication of his first three laws, he noticed that since the Earth's gravity makes objects accelerate, gravity must be a force like any other. Thus, as the story goes, as he's watching an apple fall under the apple tree, it fell to the earth because the earth exerted a force on the apple. But if he believes his third law, if the earth pulls on the apple must also pull on the earth. So Newton's genius was to realize that if the apple could pull the earth, it could probably pull anything else as well. So he hypothesized that all matter attracts all other matter. Now, Newton's law of gravity is an inverse square law, which just means the force is proportional to the 1 over the square of the distance between them. So it shows that gravity gets weaker as things move apart, which is opposite as, say, the force of a piece of elastic, which gets stronger as it's stretched. If you take a rubber band, it's very easy to stretch it at first, and it gets harder and harder. So the force between two objects can be measured in the lab, but it's difficult because the force between these two small bodies is very weak. That letter G, I said, is the universal constant of gravitation. We look it up. As far as we know, it's the same everywhere in the universe. So one of the greatest successes of Newton's law of gravity, coupled with his other laws, is that it explained how orbits work, both qualitatively and quantitatively. So in Newtonian physics, the reason the Earth is in orbit around the Earth is the force towards the center of the Earth continually pulls the object toward the center of the Earth, but its forward motion carries it away from the Earth. And Newton was able to explain this using something called Newton's cannonball. If I, say, had a very tall mountain on the Earth, and I shot a cannonball off, it would come and would fall down. Let's put more gunpowder in. Next time it'll go a little bit further before it strikes. And I could continue to do this every time, making it go a little bit further, a little bit further. If I shot it with enough speed, though, as it goes around, it's falling towards the Earth, but its forward motion takes it around until it eventually comes back to where it was. So satellites don't fall out of the sky because they're moving fast, about 18,000 miles an hour in case of the space shuttle. So once you get them to the right speed, they're going to stay there indefinitely, or at least until the small amount of friction caused by the little bit of atmosphere up there slows it down. One of the useful features of Newton's laws is that we can now measure how an object moves in a distant orbit, and if you can do that, you can measure the mass of the object. So for example, we can get the mass of Jupiter from measuring the orbits of its satellites. Newton showed that if you start with his four laws and consider a small object in orbit around another object, you can derive all three of Kepler's laws exactly mathematically. It's not easy, so Newton invented differential calculus in order to solve this problem. And we note that Newton's laws are much more fundamental than Kepler's, so they provide an explanation for the shapes. If nature follows Newton's laws, the planets must travel in ellipses. And second, they allow for situations that can't be dealt with Kepler's laws. So let's look at a couple of these examples. Comets. Newton's contemporary Edmund Halley recognized that you could apply Newton's laws to the motion of comets, which were nothing like circles. Some comets travel in parabolas or hyperbolas, which are really foreign to Kepler's laws, but they're entirely predictable by Newton's laws. In fact, Halley predicted the 75-year return of the comet that bears his name. He actually died before it got here, but when it came, it justified both his work and Newton's work. The other thing that Newton's laws give you is perturbations. So if you look hard enough at the orbits of the planets, you'll find they're not exactly ellipses. For example, as Mars goes around by Jupiter, it actually kind of moves out a little bit and back in, kind of this bump as it goes past Jupiter. So there are gravitational forces between the planets as well as between the planet and the sun. Those extra forces perturb the motion of the planets away from being a perfect ellipse. Newton's theory tells us exactly how to deal with this problem, while Kepler's laws don't deal with the situation at all. Kepler's laws deal with the problem of one or more small objects orbit around a larger one. But it's possible for two objects of comparable mass to orbit around each other, as we'll see in binary star systems. Newton's laws have no problem with this. Both objects are in elliptical orbit around an imaginary point in space called the center of mass. In fact, we can now use this principle to detect planets around distant stars that are too faint to be seen directly. So as the planet orbits the star moves in a small orbital motion which we can detect and determine there's a planet and how big the planet is. And finally, any civilization that lives near the ocean can make the link between tides and the moon. The times of high tide vary in a similar way to the times that the moon transits the meridian. But until Newton's time, it wasn't realized that the connection between the moon and the tides was gravity. Newton's theory can explain the timing of the tides, why there are 2 tides a day, and account for the effects of the sun's pull as well as the moon's. This is a good example of a scientific theory that was developed for one purpose being successfully applied to another phenomena. To understand why there are 2 tides a day, one has to consider the balance between gravitational force of the moon and the centrifugal force on the water. These together produce bulges on both sides of the Earth. So as the Earth rotates under the bulges, a person standing on the shore experiences 2 tides each day. The sun also raises tides about 1/3 of the size of the lunar tides. They sometimes add to the moon's and sometimes neutralize it, depending on the time of the month. The sizes and timing of the times depend on where you are. But tides can easily reach 20 to 30 vertical feet in some places of the world.